Hello, welcome again to the Future Internet course. We are in the unit of data plane programmability, and we explained a little bit in the last video the motivation for the data plane programmability. And we ended here in the P4, Programming Protocol Independent Packet Processors. P4 is actually a domain-specific language. It is a language, programming language for specifying packet processing by programmable switches. And this is the first programming language for programming any programmable switch. So if your switch is able to support P4, you can program any characteristic, any feature that you want from this switch. We're going to see this in more detail. It is designed with three main goals. First, the reconfigurability. It should be possible to change the way switches process packets after they are deployed. So no more fixed function switches, no more switches that just recognize the standard protocol. So if you want to add a new protocol or a new data plane label to a packet, you can reconfigure your switch so the switch is able to understand this new label, and then you can also decide what to do with the label in the switch. It also has protocol independence because a switch should not be tied to specific packet formats. Rather, a program should specify how a switch processes packets, and also how a switch or which formats or which protocols will be recognized by the switch. We also need target independence. The programmer should not need to know all the details of the underlying switch, just need to know how to program it with a common language like P4. So in P4, what we have here inside the switch or the chip of the switch is a parser to parse or to recognize the fields in the packets or the protocols in the packets. Then we have match and action tables. We also have the packet metadata and the queues and the scheduling that you can do in the switch. Okay. So when you have a programmable switch, in the beginning, the switch doesn't know how to talk any protocol. It only knows how to extract a field, right, from the packet, or match some values, or modify a field. So with this information, you can actually program which are the fields that you're going to match and what are you going to do when you match on those fields. So you can parse those fields and then establish the match and action rules, right? That can also, of course, come from the control plane. So a P4 program defines the following. First, in the parser, here, what are the headers that the switch should know? So for instance, in the switch, I can parse an Ethernet header or an IPv4 header or a VLAN header, or you can put any label, any layer that you want in the OSI stack. So you can also parse TCP headers or custom headers that are new headers that you insert to your packets. So in this way, you can actually customize the behavior of the switch. So this is something the switch defines. Also, when should the switch parse each header? So which is the header that is expected first, for instance, first Ethernet, and then, for instance, maybe VLAN or maybe IPv4 or maybe the custom one. So you can like program this order or yeah, actually program the order saying when the switch should parse each header. The P4 program also defines how the switch should process packets according to the information gathered from the parse headers. So you have the match and action tables that are already maybe installed from the control plane, are already maybe there. And the switch, so you can tell the switch how to process the packet. So if the packet is an, I don't know, IPv4 address in this range, so I can do the match here, and the action will be this one. And you can also define new actions, so not just the actions that the OpenFlow protocol is limited to, like discard or queue or whatever. You can define new actions, so it's very, very flexible. And you have here the packet processing in the match and action tables, and also you can count with packet metadata to do this match and action process. Packet metadata, like for instance, from which physical port the packet came or entered the switch. What the P4 program does not define is the queues and scheduling. This is not configured by P4. It's configured at runtime, and this is the thing that is already there in the switch, so cannot be configured by P4 and is outside of the scope of this programming language. Okay, this is the, I would say, the SDN 2.0 architecture with P4. So I would call, and a lot of people call P4 the OpenFlow 2.0. So it's the new version of OpenFlow, because actually P4 is a program that you write here, as you see here, as a .p4 file. This file is compiled by the P4 compiler, which actually exits a .switch code file and a .p4 info file, which goes actually to the control plane or to the network operating system or to the controller with P4 support, right? Then with this P4 program, you are saying my switch is like this and can accept this kind of header, this kind of protocols, and so on and so on. Anyway, the control plane has on top of it the application, the monitoring, routing, or any application running on top of it. And then the communications between the switch, between the control plane and the data plane, so the southbound interface. But before were OpenFlow, now it's P4. So what you do is you install and update switch code through something called P4 runtime to the programmable switch. And you can also install or actually query forwarding rules, not just the switch code, but also, let's say the switch code is the new thing. The new thing saying, okay, you are going to behave as this switch. But also you have the installing and querying forwarding rules through the P4 runtime, which was the same ability or capability that OpenFlow had before, right? So besides having this capability, it's also P4 also has the capability of telling the switch how to behave or what kind of switch you are, right? So this is the architecture with P4. Let's talk a little bit of some applications of P4. Let's say the first one is the optimizing resources and reducing complexity. Actually, what one may think is that with P4 you're going to put a lot of more extra custom, let's say, headers to and new, let's say, functionalities for the switch. But one actually good application is to reduce complexity. When you have a traditional switch, this is an example of what you have in IPv4, IPv6 routing. All this comes with the switch, which makes it very complex. IPv4, IPv6, Ethernet switching, load balancing, fast failover, tunneling, MPLS, ACLs, quality of service, NAT, security, and so on and so on and so on. But maybe in your network you don't need all these functionalities. You just need some of those functionalities for the applications or for the services that you're running. So maybe you don't need all these functionalities, you just need a set of them. And with P4 or with programmable switches, you can just configure the functionalities that you need in the switch, making the switch less complex, or making the switch having to, let's say that decreasing a lot the burden and the load in the switch in terms of the number of functionalities and resources that the switch has available, right? So this is a very good application, optimizing resources and reducing complexity. Another very nice application is network telemetry. With something like programmable switches, programmable data planes, and things like P4, you can do some things as, for instance, network telemetry. Uh, if I want to have complete visibility into exactly what our network or my network is doing all the time, maybe I have to answer some questions. For instance, this question, I have this pad, right? And I would like to know with my packet there, starting here and ending here, I would like to know, for instance, which was the path that my packet took, right? Which path did my packet take? I want to know which was the path, right? I, I, I want every packet to tell me maybe which are the switches it visited and when. Another good, for instance, it would be good if my packet can say, okay, I visited switch 1 at this time, switch 9 at this time, and switch 12 at this time. No, now I know two things. I know the path and the delay that my packet had. Another question, which rules did my packet follow? So inside each switch, I would like my packet to tell me, hey, I took the switch, I did match in the flow table of this switch in the rule number 75. In this other switch in the rule number, I don't know, 2, and this other switch in my rule number 3. And this would be very good for troubleshooting and detecting problems that could be there in the configuration of the switches, right? So this is another question that can be answered actually, as we're going to see with the data plane programmability. Another question could be, how long did my packet take? Did my packet queue or take at each switch, right? How long did my packet spend in the queue at each switch along the way? It would be very good if every packet can tell me how long it was sitting in a queue, right? For instance, it can tell me, okay, the queue of the first switch was 100 nanoseconds, the second switch 200 nanoseconds, but the third switch almost 20,000 nanoseconds. So I know now that there is some kind of delay or bottleneck in this third switch, right? So something happened, right? Because look at the time in the queue in this switch. And how about this another question? Who did my packet share the queue with? So if I see a queue very large, so what happens, right? It's very important to know if the queue is very large to see what are the other packets that actually my packets share the queue with, to see where is the congestion, right? And to identify maybe aggressor flows. So this is something I can answer these 4 questions with a programmable device. Potentially can answer all these 4 questions at line rate. This is very important, with something called in-band network telemetry. So with something like programmable data planes or P4, I can put inside the packet information like switch ID, arrival time, queue delay, match rules, and so on. If I can program the switch to put this information inside every packet, this is very nice. And then I can put here, for instance, a log to analyze, to replay. And then in the end, I can just pop these labels and just deliver the original packet. So this is a very powerful tool as an application. Network telemetry, in-band network telemetry inside the network with something like programmable data planes. In the next class, and to visualize the information. This is one example of P4 code to do this network in-band telemetry. Anyway, in the next class, we're going to start into the details. We're going to be very brief, but we're going to see some of the main details of P4, and we're going to make the first implementation of P4 in the next class. So thank you very much for your attention, and let's see each other in the next class.